On clear summer nights, we have marveled at a luminous band stretching across the sky, unaware of the dynamic forces shaping the universe behind this cosmic veil of gas and stars. Two groups of astronomers are currently investigating a star whose unprecedented speeds might hold clues to the enigmatic object concealed within our galaxy. This object, believed to be a supermassive black hole, resides in the densely packed central bulge of the Milky Way. Our galaxy, when viewed from distant space, appears as a flat spiral with approximately 200 billion stars, swirling gases and dust forming vast arcs. The central bulge, filled with stars, has long been obscured by dust and bright starlight, intriguing astronomers about its mysteries. In the 1930s, physicist Carl Jansky, tasked with identifying sources of radio static, discovered an unexplained radio noise in the direction of Sagittarius, near the galaxy's center. Despite Jansky's finding, the nature of this signal remained elusive for 3 decades. In the 1960s, astronomer Erich Becklin, driven by curiosity, aimed to explore the galactic center further. Using infrared light to penetrate the dust obstructing the view, Becklin measured its intensity, pinpointing the center of the Milky Way. Concurrently, Reinhard Genzel and his team embarked on a similar quest, using advanced telescopes and technology to unravel the mysteries of Sagittarius A*, the potential supermassive black hole. In 1993, using the Keck telescope in Hawaii, Becklin and colleagues tracked the motion of stars orbiting Sagittarius A*. Their precision allowed them to position stars within a 2 centimeters accuracy, unveiling a dense and dim region at the galactic center. Simultaneously, astronomers observed the giant elliptical galaxy an 50 million light-years away using the Hubble, Spitzer, and Chandra telescopes. These observations revealed heated gas arcs, infrared signatures of star concentrations, and high-energy radiation sources, likely neutron stars and small black holes. The Chandra X-ray Observatory estimated that the inner 3 light-years of the galactic center might harbor around 20,000 black holes. This comprehensive study of our galaxy's center forms part of a broader effort to map its layout, unravel its history, and train powerful telescopes on the galactic center as part of the Great Observatories project. The collective findings contribute to a deeper understanding of the dynamic forces shaping the Milky Way and offer insights into the existence of a supermassive black hole at its heart. In the heart of the galactic center, where stars surround us in every direction, the environment is hostile and intense. The presence of massive stars emitting radiation, collisions between gas clouds, and occasional material releases from the supermassive black hole make it a challenging space. To confirm the existence of this black hole, scientists needed to demonstrate its confinement to a small region and its ability to accelerate orbiting stars to high speeds. The light from these stars, traveling 26,000 light-years, faces distortion in the Earth's atmosphere, blurring their apparent positions. To overcome this, both teams adopted methods to capture thousands of images rapidly. By averaging positions and analyzing the wavelength of starlight, they calculated star speeds, reaching an astonishing 10,000 kilometers per second during closest approach. This data allowed them to narrow down the black hole's position and estimate its gravitational strength, approximately 3 million times that of our Sun. Although strong evidence, it wasn't conclusive proof, as a dense star concentration remained a potential explanation. A breakthrough came in 2002 when the star S2, observed by both teams, exhibited a dramatic acceleration, reaching 18 million kilometers per hour. Its proximity to the suspected black hole, about 3 times the distance between the Sun and Pluto, ruled out a star cluster's influence. This event confirmed Sagittarius A* as a singular black hole, weighing around 3 million times the Sun's mass. This revelation coincided with a broader understanding that supermassive black holes play a crucial role in galaxy evolution. They occupy central positions in large galaxies, with their size correlating to the galactic bulge surrounding them. As matter flows into a black hole, intense winds and jets are produced, influencing a galaxy's growth by limiting starbirth and pushing gas away. Scientists turned their attention to the Milky Way's black hole, seeking to determine if it is still active and growing. Observations in 2001 and subsequent focus with the Chandra X-ray telescope reveal flares or outbursts, indicating an active black hole. The recurring accretion events, or gas spirals into the innermost regions, offer insights into the black hole's behavior. In 2021, astronomers are planning to use the Event Horizon Telescope, linking observatories worldwide to create an Earth-sized radio telescope. This collaboration aims to capture detailed images of the supermassive black hole's silhouette and surface eruptions, providing a deeper understanding of its periodic changes and overall dynamics. Over a specific timescale, the materials orbiting the black hole provide crucial information about its characteristics. The time it takes for these materials to complete an orbit around the black hole indicates their proximity, and this parameter becomes significant in understanding the black hole's rotation. In a non-rotating black hole, the shortest period detectable is around 24 minutes. However, if the black hole is rotating, material from the accretion disk can get closer, revealing the influence of the black hole's spin. Simultaneously, astronomers are conducting an extensive study to map the turbulent environment of Sagittarius A*, aiming to unveil its current state and potential changes. Utilizing space observatories like Hubble, Spitzer, and Chandra, they have produced a detailed image of the galactic center. The central zone, spanning 160 light-years, resembles a vast claw, with Sagittarius A* identified as the X-ray heart region. The Arches cluster, containing about 1,000 stars, and the Pistol star in the quintuplet cluster contribute to the intense stellar activity in this region. Large stars, such as the Pistol star, generate powerful plasma winds, forming the galactic center's environment. Monitoring X-ray emissions with the Chandra telescope, astronomers observe that these stars are slightly too distant to provide substantial feeding material for the black hole. The outward wind generated by the heating process blocks a significant portion of inflowing material, raising questions about what triggers a flare-up. Another study proposed that instead of gas, comets and asteroids stripped away from stars on close orbits might be falling into the black hole. The black hole, currently in a state of semi-retirement, may become active again under specific conditions. Radio astronomers in the Antarctic have identified signs of a potential flare-up, with a massive ring of gas accumulating beyond the galactic center. Once it reaches a critical mass, this gas cloud will funnel into an inner ring, eventually spiraling down toward the black hole, resulting in a spectacular eruption visible across the universe. While anticipating these astronomical phenomena, astronomers continue to explore the broader region surrounding the galactic center. They have identified a smaller cloud on a rendezvous with the black hole, and simulations show it getting torn apart as it passes by. The momentum of this cloud will likely carry most of its mass swirling past the black hole, settling into an orbit and gradually collapsing toward the center. In their observations from a distant outpost 25,000 light-years away, astronomers remain vigilant for unexpected events. Tracking patterns of change over billions of years, they find wonder in both significant and seemingly insignificant occurrences. Objects like the star's 2 completing orbits around the galaxy's center every 16 Earth years and its counterpart S-102 circling every 11.5 years provide valuable insights. As these stars continue their orbits, they hold the potential to answer fundamental questions about the supermassive black hole's formation, its impact on the galaxy, and the mysteries of the universe's origin and evolution. A fleet of advanced instruments was launched into space above Earth's atmosphere decades ago to delve into the most violent phenomena in nature and unravel the mysteries of the high-energy universe. High-energy astronomy emerged driven by fundamental questions about the existence of supermassive black holes, the nature of quasi-stellar objects, quasars, the origins of diffuse X-ray glows, the occurrence of bursts of ultra-high-energy gamma radiation, and the exact nature of supernovae. These questions led scientists to explore whether supermassive black holes are real and whether quasars are solitary entities in the vast darkness or part of larger structures. In the early 80s, a diffuse X-ray glow was observed filling the night sky, prompting investigations into its origin. Events involving bursts of ultra-high energy gamma radiation were also a focus, raising questions about their proximity to our solar system and their level of energy. Astronomers suspected that supernova violent explosions held the key to understanding the cosmos. It was later revealed that supernova marked the final moments in the lives of massive stars, contributing to the elements that constitute our bodies, such as calcium, iron, and carbon. High-energy light, which doesn't penetrate Earth's atmosphere, necessitated the launch of space observatories covering a range of wavelengths from gamma rays to infrared. These observatories provided insights into the temperature of celestial objects, with gamma rays and X-rays indicating temperatures in the tens to hundreds of millions of degrees. Ultraviolet, visible light, and infrared revealed temperatures in hundreds of thousands to hundreds of degrees. For instance, the Hubble Space Telescope captured the visible remnant of a supernova at about 10,000 to 20,000 degrees Celsius, while the Chandra X-ray Observatory showed gas heated to tens of millions of degrees. In 1994, the Hubble telescope unveiled the galaxy M87, displaying the hot gas swirling around its core. This discovery led to the realization that supermassive black holes exist at the center of large galaxies, including our Milky Way. A black hole's powerful gravity tearing apart a star creates an accretion disk of hot gas and dust, generating jets moving at nearly the speed of light. The inner parts of the accretion disk, hot and bright enough to shine as quasars, become intense sources of high-energy gamma and X-rays. The most active quasars likely consume matter at a high rate. Images from the Hubble telescope revealed radio jets emanating from the centers of galaxies, showcasing accretion disks resembling CERN's dark tower. Black holes, often perceived as invisible sources of destruction, exert such powerful gravitational forces that they distort the fabric of spacetime. Approaching a black hole reveals an accretion disk visible from above and below, featuring an inner ring caused by light encircling the black hole before escaping. Understanding how gas orbits the event horizon involves magnetic fields, sapping angular momentum, allowing some gas to fall in while expelling the rest into space. Magnetic fields near black holes can stretch and snap, releasing massive energy and heating gas to millions or billions of degrees. This phenomenon, akin to a roller skating maneuver, involves transferring angular momentum and shedding gas into space, contributing to the dynamic and fascinating nature of black holes. The magnetically active corona of our Sun exhibits superheated gas that emits intense X-rays. Einstein's theory of relativity predicts the remarkable effect of a black hole's extreme gravity, illustrating the twisting of spacetime. In simulations of particles plunging into a black hole, this twisting is evident outside the event horizon, causing a counterclockwise swirl at nearly the speed of light. The gravitational forces, twisting, and slinging of gas by black holes result in ultra-high energy particles and powerful jets, showcasing the fascinating predictions of Einstein's theory. The New Star mission marks the first telescope observing the universe in high-energy or blue X-rays. An image from the Hubble Space Telescope depicts the nearby galaxy Messier 82 in black and white, highlighting warm, dusty regions visible in red, orange, and yellow if observed in visible wavelengths. The blue reveals hot regions where stars actively form. New Star made high-energy X-ray images around the supermassive black hole at the Milky Way's core, uncovering a hot haze from a swarm of dead stars. When the universe began, it comprised a hot soup of hydrogen and helium gas. Over 13.8 billion years, this evolved into a diverse mix of chemical elements, from nitrogen in the atmosphere to calcium in bones. Simulations using supercomputers illustrate the universe's evolution, with filaments of hydrogen and helium forming under the influence of dark matter. Clouds of dust and gas condense in these filaments, giving rise to stars that in turn produce heavier elements through nuclear fusion. Supernova explosions disperse these elements into space, contributing to the formation of galaxies, stars, and planets. The collaboration between theorists and observers, armed with various telescopes and computational resources, has deepened our understanding of stellar life cycles. Simulations, like one depicting a stellar explosion, aid in comprehending natural phenomena. X-ray telescopes capture images of supernova remnants, such as Cassiopeia, revealing the bubbly shape consistent with theoretical predictions. The realm of high-energy telescopes in space unveils violent events in unprecedented ways. Gamma-ray bursts, the most energetic explosions in the universe, occur approximately once per Earth day. Early speculation about these bursts included notions of aliens and outer space wars. However, Swift and Fermi satellites have since detected over 1,000 bursts, revealing their origin in supernovae, highlighting the extreme brightness and energy of these events. With every gamma-ray burst detection, scientists analyze data to unravel the secrets of these powerful phenomena. The intricate dance between observations and theoretical predictions, facilitated by a range of telescopes and advanced technology, continues to deepen our understanding of the dynamic and violent processes shaping the universe. Black holes form when the cores of massive stars collapse, and a fraction of the matter flowing into the black hole escapes in jets. When these jets are directed toward us, they manifest as gamma-ray bursts, which are so intense that they have the potential to obliterate the atmospheres of nearby planets. Despite the intensity of these phenomena, Earth appears to be safe, at least for the time being. Consider a scenario of a dark and clear night, where the Milky Way stretches across the starry sky, inviting us to ponder the nature of our marvelous universe. The vastness of space prompts us to question its origins and our place within it. Astrophysics, the study of the universe and its workings, becomes pivotal in our quest for answers. Instruments like Fermi, Swift, NuSTAR, and Chandra, sent beyond our atmosphere, reveal a dynamic universe vastly different from the serene view we perceive with our eyes. These instruments uncover turbulent forces such as black holes, cosmic explosions, and bursts of radiation, emphasizing that violent energy is an integral part of the cosmic tapestry. As we delve into the profound questions about the universe, we recognize that what we observe is just the beginning of a story written in the cosmic rumbles of the cosmos, a story still unfolding. The year 2017 proved to be significant for scientists, with both professionals and enthusiasts witnessing astronomical rarities and surprising discoveries. Breakthroughs challenged long-standing beliefs and provided glimpses millions of years into the past. In August 2017, the Laser Interferometer Gravitational Wave Observatory, LIGO, in Washington state detected gravitational waves, marking a groundbreaking moment in scientific history. These waves, ripples in space-time caused by objects with immense gravity, such as black holes or neutron stars, reached Earth. This discovery prompted collaboration with Virgo, LIGO's European counterpart in Italy, confirming the detection of gravitational waves. 2 seconds later, the Fermi Gamma-Ray Space Telescope observed a short, bright flash of high-energy light known as a gamma-ray burst. This event set the astronomical community abuzz, leading to extensive observations by 70 ground and space-based telescopes focused on galaxy NGC 4993, located 130 million light-years away. This collaborative effort unveiled the merging of two neutron stars, resulting in a cataclysmic explosion that generated gravitational waves, gamma rays, and various forms of light. Neutron stars, remnants of massive stars after supernova explosions, are incredibly dense and possess 10 to 60% more mass than the Sun within a compact size. The collision of these neutron stars, orbiting each other for over 11 billion years, created an extraordinary explosion observed by telescopes. The aftermath displayed a sequence of colors, from a bright blue flash to a progressively redder and dimmer glow, ultimately fading away. This celestial event, seen as one of the universe's spectacular fireworks, allowed astronomers to glimpse into the past and witness the remnants of a cosmic collision. The conditions surrounding the merging of neutron stars provided invaluable insights into the dynamic and evolving nature of our universe. The year 2017 not only brought forth groundbreaking discoveries, but also emphasized the intricate interplay of cosmic forces that shape the cosmos we seek to understand. Zealandia is mostly submerged beneath the ocean's surface. Neutron stars exhibit densities and temperatures that are beyond replication on Earth. A violent explosion involving neutron stars was observed to produce significant amounts of heavy metals, specifically 200 Earth masses of gold and 500 Earth masses of platinum. This groundbreaking observation sheds light on the origins of heavy metals in our galaxy, suggesting that explosions of this nature are responsible for the formation of gold in the universe. The aftermath of these explosions disperses the newly formed heavy metals into the interstellar mediums gas and dust, eventually leading to the creation of new stars and planetary systems. The gravitational waves detected by LIGO were not limited to the neutron-star merger. Prior to this event, two separate occurrences were measured involving the collision of monstrous black holes that resulted in a single spinning hole 53 times more massive than the Sun. The perfect signal received from this merger traveled an astonishing 3 billion light-years to reach us. Although such events might occur only once every million years in a given galaxy, advancements in technology enabled the monitoring of approximately 10 million galaxies simultaneously, marking a new era in astronomy. While the study of gravitational waves provides a unique window into the universe's origins, volcanic activity off the coast of Japan offers scientists a glimpse into Earth's early history. The eruptions near Nishinoshima Island, which rapidly expanded its size, ceased in August but remain a potential area for resumed activity. Situated at the convergence of four tectonic plates, Japan provides valuable insights into the geological forces shaping landscapes and continents. In February 2017, geologists discovered Zealandia, a hidden continent submerged beneath the Pacific Ocean. Initially overlooked, Zealandia was revealed through geological investigations, meeting the criteria for a continent: significant height, varied geology, a thick crust, and sufficient size. Zealandia, measuring at 4.9 million square kilometers, is 6 times larger than Madagascar and more than twice the size of Greenland. Its existence challenges the traditional notion of 7 continents, expanding the world map to include an 8th continent. Geological markers, including rock samples, ocean drill cores, and satellite measurements, confirm Zealandia's continental status. Positioned between the Pacific Plate and the Australian Plate, Zealandia emerged when tectonic forces squeezed it out of the water, forming what we now recognize as New Zealand and New Caledonia. The understanding of Zealandia's origins requires a journey back in time to the supercontinent Gondwana, which split apart 80 million years ago. Zealandia, akin to stretching bread dough, broke off and sank due to its relatively thin continental crust. This thin crust, while thicker than ocean crust, explains why Zealandia remains mostly submerged, sitting at a lower elevation in the mantle. In conclusion, these scientific revelations, from the origin of heavy metals through neutron star explosions to the discovery of Zealandia as a hidden continent, underscore the dynamic and intricate processes shaping both our universe and our planet. As technology advances, our understanding of these phenomena continues to deepen, paving the way for further exploration and discovery in the realms of astrophysics and earth sciences. Samples have provided new insights into the events that followed the catastrophic impact. In recent years, researchers have been focused on uncovering the mysteries surrounding the mass extinction event that marked the end of the Mesozoic era. The revelation of Zealandia, a submerged continent, has sparked enthusiasm within the scientific community. Efforts are underway to integrate Zealandia into educational materials, particularly in New Zealand schools, and to enhance its recognition globally. The novelty of discovering such a significant geological feature hidden for an extended period has captured people's imaginations, challenging the conventional understanding of continents. On a different note, a remarkable paleontological discovery in northern Alberta, Canada, has provided a unique window into prehistoric life. The near-perfectly preserved remains of a 110-million-year-old armored dinosaur, known as the nodosaur, offer unprecedented insights into the anatomy, coloration, and lifestyle of these ancient creatures. The fossilized specimen, often referred to as the Rosetta Stone for armored dinosaurs, has become a pivotal source for understanding the evolution and diversity of these fascinating creatures. The nodosaur's remarkable state of preservation goes beyond mere impressions of its skin, as original biomolecules have been identified. This has allowed scientists to discern the coloration of the dinosaur, revealing a reddish-brown pigment. The coloration, in turn, provides clues about the nodosaur's adaptation strategies, such as countershading for camouflage. The presence of such intricate features on a heavily armored, plant-eating dinosaur challenges preconceived notions about the Cretaceous ecosystem's intensity, highlighting the need for effective defensive adaptations even among herbivores. The nodosaur's anatomy, characterized by rows of osteoderms and a prominent periscapular spine, attests to its robust defense mechanisms. The ongoing research into the contents of the nodosaur's stomach promises to unravel more about its dietary preferences and potential relationships with flowering plants. This further fuels the exploration of how dinosaur diversification might be interconnected with the evolution of flora during the Mesozoic era. While the nodosaur's discovery sheds light on the appearance and lifestyle of specific dinosaur species, the broader context of mass extinctions in Earth's history remains a topic of significant interest. The Yucatan Peninsula's impact crater, resulting from a massive asteroid collision 65 million years ago, marked a pivotal moment in Earth's history. Seismic images and core samples from the crater contribute to a deeper understanding of the cataclysmic events that unfolded, leading to widespread extinctions, including that of the dinosaurs. In conclusion, these scientific endeavors, from the exploration of Zealandia's hidden continent to the detailed analysis of a remarkably preserved nodosaur fossil and investigations into ancient mass extinctions, showcase the continuous pursuit of knowledge in unraveling Earth's geological and paleontological mysteries. As researchers delve into these discoveries, they not only expand our understanding of the past but also contribute to the ongoing narrative of Earth's dynamic history. Deep within the archaeological site at Chicxulub, samples have provided crucial data that paints a grim picture of destruction. This data has led scientists to formulate a comprehensive survival theory, focusing on the adaptability of habitat and diet when dinosaurs faced extinction. The emergence of a vast new ecospace following the extinction event allowed surviving species to rapidly expand and diversify, a phenomenon known as adaptive radiation. Recent studies have delved into the survival strategies of various species in the aftermath of the Cretaceous-Tertiary extinction event. For instance, frogs, with their aquatic habitat providing protection, small size, and unique metabolism, were among the survivors. Their ability to endure environmental stress and later diversify globally and adapt to new environments, such as trees, showcased the power of adaptive radiation. Similarly, birds exhibited adaptive radiation during the same period. The discovery of a 62-million-year-old mouse bird fossil in New Mexico contributed to mapping the diversification of land birds. Warm-blooded with feathers for insulation, small size for easy escape, and a versatile diet of seeds, worms, and insects gave birds a survival edge as they adapted to a changing environment. The ability to adapt to changing conditions emerged as a key characteristic for the survival of many ancient animals. This adaptability, witnessed in various species, echoes the challenges faced by humans today in the context of climate change. The concept of adaptive radiation continues to be relevant as we confront the impacts of environmental transformations. In a modern context, the city of Miami Beach exemplifies the proactive approach required to address sea level rise, a consequence of climate change. Residents have experienced elevated high tides, known as king tides, providing clear evidence of incremental increases. Recognizing the severity of these events, Miami Beach has committed significant financial resources, $400 to $500 million, to combat sea level rise. Infrastructure improvements, including water pumps and elevated seawalls, showcase the city's commitment to adapting to the future challenges posed by climate change. The global issue of rising sea levels extends beyond Miami Beach, impacting coastal regions worldwide. The multi-pronged approach adopted by Miami Beach reflects the need for comprehensive strategies to mitigate the effects of sea level rise. The city's philosophy revolves around rising above challenges, both in terms of elevation and resilience, to withstand the impacts of climate change. Looking back at Earth's history, the rise and fall of oceans have been recurring phenomena. Archaeological evidence is now suggesting that shifting shorelines may hold clues about the earliest Americans. Contrary to the long-standing belief that the Clovis people were the first inhabitants of North America around 12 to 13,000 years ago, a group of scientists in San Diego proposes a radical theory. They present evidence indicating human presence in North America as far back as 130,000 years ago, a claim that has sparked controversy within the scientific community. The study of early humans in the New World has been both political and contentious for over a century. The mystery surrounding the earliest Americans remains an ongoing quest for archaeologists, with new discoveries challenging established narratives and prompting a reevaluation of our understanding of human migration and settlement in North America. Thank you for joining us at the San Diego Natural History Museum, where we are thrilled to share a significant discovery made right here in San Diego. In 1992, during State Route 54 improvements, our field paleontologist Richard Cerruti observed an excavation on the north side of the freeway. A puff of tusk material caught his attention, leading to the unearthing of bones belonging to an ancient mastodon. These mastodon bones, characterized by a distinctive tooth, raise questions about whether these giants coexisted with early humans in North America 130,000 years ago. The positioning of bones and tools found at the site, including fragments of tooth enamel and stones, hints at the possibility of primitive tools being used by early humans for butchering mastodons. To better understand the site, a meticulous mapping effort was undertaken, plotting the precise positions of bones and stones. The stones found with the mastodon bones were hypothesized to be early tools used by humans for recovering raw materials. The striations on the stones indicated potential usage as hammerstones. Dr. Stephen Holen, co-director of the Center for American Paleolithic Research in South Dakota, was part of the team evaluating the findings. Examining mastodon bones and stone tools, the team engaged in detective work, scrutinizing fracture patterns and conducting experiments, including one in Africa, to understand the potential human involvement in bone breakage. The crucial age dating conducted by Richard Cerruti confirmed the antiquity of the mastodon bones, with over 100 microsamples analyzed, yielding an age of 130,000 plus or minus 9,000 years. Despite the groundbreaking nature of these findings, there has been no credible critique challenging the accuracy of the dating, and specialists in uranium series dating have expressed confidence in the results. This discovery challenges previous notions about the timing of human arrival in the Americas, suggesting that it might have occurred much earlier than previously believed. The San Diego Natural History Museum continues to be at the forefront of unraveling the mysteries of our past, pushing the boundaries of our understanding and reshaping the narrative of human history in North America. Enhancing the well-being of individuals facing mobility challenges, such as the elderly, disabled, and obese, is a paramount goal. Addressing the barriers to physical activity, researchers are exploring the potential of small molecules to emulate the benefits of exercise without the need for actual training. This innovative approach holds promise for a broad spectrum of individuals who, for various reasons, find it difficult to engage in traditional forms of physical activity. Transitioning from individual health to global energy solutions, the pursuit of nuclear fusion stands out as a groundbreaking endeavor. The Column Fusion Center in Oxfordshire, Britain, houses the Joint European Torus, JET, a crucial donut-shaped plasma containment vessel. This facility enables scientists to replicate the conditions of the Sun, achieving temperatures exceeding 200 million degrees. Through nuclear fusion, the fusion of hydrogen atoms, researchers harness the immense energy generated when deuterium and tritium collide at extreme temperatures. Fusion is considered an ideal method for producing energy, and the experiments conducted at JET are at the forefront of this transformative energy source. Despite the enormous potential of fusion as a safe and sustainable energy solution, uncertainties loom over its future. While the British government has committed to funding experiments until 2020, the impending Brexit, the UK's departure from the European Union, introduces uncertainties regarding the country's continued participation in scientific collaborations like Euratom. This geopolitical shift could impact the logistical and operational aspects of JET and potentially hinder the construction of the next-generation fusion experiment in southern France. Shifting from the scientific realm to celestial wonders, the first total solar eclipse over North America in 3 decades captivated millions. The rare cosmic event, witnessed along a 70-mile-wide path, mesmerized spectators from the Oregon coast to South Carolina. This natural phenomenon, though scientifically explained, evoked an emotional response, highlighting the profound impact such occurrences have on individuals. Delving into the depths of the Earth, we explore Mexico's Naka mine, where cave chambers lie 300 meters below the surface. Within these chambers, colossal razor-sharp crystals dwarf human explorers, creating an otherworldly environment. Despite the extreme conditions, astrobiologists like NASA's Penny Boston venture into this challenging realm to discover life forms that exist nowhere else on Earth. The extremophiles found within these crystal giants open new possibilities for understanding life's limits and contribute valuable insights to the search for life beyond our planet. Boston's discoveries extend to astrobiology's application in extraterrestrial exploration, with implications for the search for life on celestial bodies like Ceres, the largest object in the solar system's asteroid belt. The Dawn space probe's exploration of Ceres revealed unexpected spectral signatures, suggesting the presence of aliphatic hydrocarbons, building blocks of biological molecules. These findings expand our understanding of life's potential in diverse planetary settings. In conclusion, from advancing individual health through innovative approaches to unlocking the mysteries of celestial events and exploring extreme environments on Earth, scientific exploration continues to push boundaries and redefine our understanding of the world and beyond. The red materials visible in this image are believed to be organic in origin and are thought to have originated within the dwarf planet itself. Dawn's study of Ceres has not only shed light on its surface composition, but also revealed signs of water and volcanic activity, challenging the previous perception of Ceres as a barren rock. Meanwhile, NASA's Juno spacecraft, which became fully operational in February 2017, has been making significant discoveries in Jupiter's planetary system. The largest planet in our solar system, Jupiter, has long been shrouded in mystery due to its thick cloud cover. Juno's microwave radiometer has provided unprecedented insights, allowing scientists to study the Great Red Spot and the planet's atmospheric environment in 3 dimensions. The data challenges previous models, revealing unexpected variations in the interior dynamics of Jupiter. The thickness of the cloud cover, the presence of a possible rocky core, and the intricate dance of metallic hydrogen in its depths are all subjects of intense scrutiny. Juno's mission, scheduled until February 2018, has already raised more questions than answers, pushing scientists to rethink their understanding of Jupiter's formation and the early solar system. In contrast, the Cassini spacecraft concluded its remarkable mission by plunging into Saturn's atmosphere in a fiery descent. Over the course of 2 decades, Cassini transformed our understanding of Saturn, its rings and its moons. The spacecraft's groundbreaking discoveries included storms of immense force on Saturn, colossal lightning strikes, and the intricate dance of particles within its dazzling rings. Cassini's Huygens probe, which landed on Saturn's moon Titan, marked the first time a probe touched down on a moon beyond Earth. The mission's grand finale, culminating in Cassini's controlled descent into Saturn's atmosphere, was a moment of both celebration and reflection for the dedicated team behind this incredible exploration. As we continue to unravel the mysteries of our solar system, these spacecraft, Dawn, Juno, and Cassini, have played pivotal roles in reshaping our understanding of celestial bodies, challenging existing theories, and inspiring new avenues of exploration. The quest for knowledge in the cosmos remains ongoing, with each discovery paving the way for future missions and further expanding the horizons of human understanding. Cassini's mission to Titan, Saturn's largest moon, began with the challenge of its thick atmosphere, gradually revealing the moon's surface as it pierced through the haze. Capturing images of giant water jets spewing from tiger stripes on Enceladus, another moon of Saturn, provided unexpected insights. Cassini's controllers, quick to respond, redirected the probe to fly through the jets, discovering organic molecules, the building blocks of life. This extraordinary find, combined with Titan's Earth-like properties, raised the possibility of microbial life evolving on the moon. As Cassini reached the end of its mission, its controlled descent into Saturn's atmosphere yielded valuable data about the planet's environment. Despite its fiery demise, Cassini's contributions continue to shape our understanding of the solar system, particularly in the ongoing search for extraterrestrial life. The discovery of the TRAPPIST-1 system, with multiple planets within the habitable zone, further fueled the quest for habitable worlds beyond our solar system. Looking ahead, astrophysicists contemplate the fate of the universe. Scenarios include the Big Crunch, where gravity pulls the universe back into itself, resulting in a dramatic end. The Big Chill envisions a universe expanding until stars burn out, leaving a cold and desolate cosmos. Another possibility is perpetual expansion, leading to a lonely existence for stars and galaxies. The most dramatic conclusion involves an ever-accelerating expansion, tearing the universe apart down to the last atom. Delving into the origins of the universe, scientists trace the mystery back to Edwin Hubble's 1929 discovery of its expansion at Mount Wilson Observatory. While the fate of the universe remains uncertain, its potential endings offer a glimpse into the grand spectacle that awaits, with scientists continually exploring the secrets of our cosmic existence. Edwin Hubble's groundbreaking discovery in the early 20th century transformed our understanding of the universe. Prior to Hubble, scientists perceived the cosmos as static and unchanging. However, Hubble's revelation that the universe is dynamic and evolving, constantly expanding, marked a paradigm shift in cosmology. Hubble's observation of the universe's expansion implied a starting point, challenging the static model. This revelation led to the concept of the Big Bang, a cataclysmic event where the entire universe, everything in it, burst into existence from a point smaller than an atom. It's crucial to dispel the misconception that the Big Bang occurred at a specific point in space. Rather, it initiated a simultaneous creation of space everywhere, perpetually expanding. The theoretical framework suggests that during the initial moments of the Big Bang, tiny particles called quarks were produced, eventually colliding to form the foundational elements of the universe. These particles existed in a hot plasma fog for approximately 400,000 years before gravity took over, bringing them together to create the first stars, illuminating the cosmos. Despite the robustness of the Big Bang theory, certain aspects, such as the precise events at the moment of the Big Bang, remain areas of ongoing exploration and investigation. Contemplating the future of an expanding universe raises questions about its eventual fate. Scientists hypothesize that gravity, a force present since the Big Bang, might play a role in determining the universe's destiny. One possible scenario involves a Big Crunch, where the universe, after expanding, reverses direction and collapses under the influence of gravity. This collapse mirrors the motion of a model rocket that rises against gravity, coasts momentarily, and then falls back to Earth. While the Big Crunch was initially considered a plausible scenario, subsequent developments in cosmology suggested the presence of an opposing force preventing the collapse. This force, attributed to a mysterious energy form, gave rise to new theories regarding the universe's composition and its potential outcomes. Black holes, among the most enigmatic phenomena in the cosmos, play a significant role in this cosmic narrative. Advanced technologies, such as the KEC telescopes atop a Hawaiian volcano, serve as tools for astronomers attempting to decipher the universe's fate. These telescopes, situated far from city lights and high above Earth's polluted air, provide an unparalleled view of the cosmos. Scientists like Richard Ellis aim to determine the universe's rate of expansion, a crucial factor in predicting its future. While challenges persist in understanding the intricacies of cosmic evolution, astronomers persist in their pursuit of knowledge, unraveling the mysteries of the universe from its distant past to its uncertain future. The revolutionary shift in our understanding of the universe, marked by Edwin Hubble's observations in the early 20th century, unveiled a dynamic, evolving cosmos. Prior cosmological views considered the universe static and unchanging. Hubble's groundbreaking discovery of the universe's expansion challenged this notion, introducing the concept of a dynamic environment that evolves over time. The newfound understanding suggested that the universe had a starting point, implying a momentous beginning known as the Big Bang. Hubble's revelation prompted scientists to contemplate running the cosmic film backward in time, pinpointing the exact fraction of a second when the universe explosively originated from a point smaller than an atom. It's essential to dispel the misconception that the Big Bang occurred at a specific point in space. Instead, it is more apt to envision the Big Bang as a simultaneous creation everywhere, initiating the expansion of space that persists to the present day. The theoretical framework proposes that during the Big Bang, quarks, the first small particles of matter, emerged, eventually colliding to form the fundamental building blocks of the universe. These particles existed in a hot plasma fog for approximately 400,000 years before gravity played a role in drawing them together, leading to the formation of the first stars that illuminated the cosmos. While the Big Bang theory stands as a robust explanation, the specifics of what transpired at the exact moment of the Big Bang remain a subject of ongoing exploration and investigation. Considering the universe's expansion since the Big Bang, scientists grapple with the possibility of it ceasing to expand at some point. The primary contender for this scenario is gravity, a force present since the Big Bang, potentially causing stars, galaxies, and the entire cosmos to reverse direction and collapse in what some scientists term a big crunch. A model rocket serves as a metaphorical illustration, offering insights into how this hypothetical collapse might occur. However, as the Big Crunch theory was set aside, cosmologists acknowledged the existence of a mysterious energy form preventing the universe from collapsing. This discovery led to new theories about the universe's composition and potential end, with black holes among the most powerful and mysterious phenomena in the cosmos, playing a crucial role in shaping these hypotheses. Predicting the universe's end requires advanced technology, and astronomers, stationed on a remote volcano in Hawaii with telescopes like the KEC, strive to unravel the cosmic fate. Despite the challenging conditions, these powerful telescopes provide astronomers with a clear view of the cosmos, enabling them to explore famous and extreme celestial objects. Cosmologists, including Richard Ellis, continue their pursuit to understand the universe's rate of expansion, a critical factor in predicting its ultimate destiny. The answers to how the universe will end lie in unraveling the mysteries of its past, presenting an ongoing scientific quest that promises to expand our comprehension of the cosmos from its distant origins to its uncertain future. Examining my actions, my primary focus was on capturing images of celestial bodies using a ground-based telescope. This approach serves as a time machine, allowing astronomers to peer into the past and study distant galaxies as they existed eons ago. In one such distant galaxy within the Cygnus constellation, astronomers discovered a potent source of X-rays emanating from an unseen entity. Despite emitting no visible light, this celestial object, later identified as a black hole, held a mass approximately 7 times that of Earth's sun. The concept of black holes serves as an analogy to the Big Crunch theory, where collapsing stars, having depleted their fuel, condense into a smaller, denser mass with a gravitational pull so intense that nothing, not even light, can escape. The notion that something invisible, like a black hole, can be detected and provides insights into our cosmic destiny is mind-boggling. A visual demonstration using a black tarp illustrates how massive objects, like a black hole or even a sun, warp the relatively flat space around them. The gravitational pull of these massive objects shapes the space, causing smaller objects, like a penny, to orbit around them in a circular path. In contrast to a black hole, the sun's gravitational pull is comparatively milder, allowing Earth and nearby planets to orbit without being drawn into the sun. Black holes, with masses reaching millions of times that of the sun, create a profound warp in space that entraps anything in proximity, symbolizing a scaled-down version of the force that could lead to the universe's collapse. Dark matter. Dark matter, often referred to as cosmic glue, exerts a positive force through its gravitational attraction, acting as a unifying agent for the cosmic structures. This force is complemented by dark energy, a mysterious negative repulsing effect that pushes galaxies away from each other. In a cosmological demonstration by Richard Ellis, the whirlpool symbolizes the gravitational force of dark matter, drawing in the green dye representing cosmic material, to demonstrate how dark matter shapes the structure of the universe. This interplay between positive dark matter and negative dark energy contributed to the development of structures like the Milky Way, formed as small entities merged into larger ones during the universe's expansion. While gravity, driven by dark matter, could theoretically cause the universe to halt its expansion and eventually collapse in a big crunch, The observed ongoing expansion implies that dark energy, the opposing force, might be stronger. To uncover the balance between these cosmic forces, astronomers turn to the study of exploding stars or supernovae, which provide crucial clues about the universe's expansion rate. These explosive events, captured by the Hubble telescope, offer a brief yet bright display that scientists use as reliable indicators to track the universe's expansion and delve deeper into the mysteries of dark matter and dark energy. To measure the speed of the universe's expansion, astronomers utilize white dwarf stars that transform into nuclear bombs, exploding with consistent brightness and duration. These exploding stars, known as supernovae, act as standard candles, maintaining uniform appearance regardless of their location in the universe. Astronomers gauge the distance and speed of these celestial explosions by analyzing the amount of red light they emit. As a star moves away from us, its light appears redder, and this redshift is a key parameter in determining the expansion rate of galaxies containing such stars. Comparing the velocities of galaxies with their distances provides crucial clues about the universe's overall outward movement. Dr. Ellis conducts observations at the Keck Observatory in Hawaii, while simultaneously, Johann Rischer is at the California Institute of Technology in Pasadena, California, examining light from a distant galaxy captured by the Keck telescope. They analyze the red spectrum to identify elements moving farther away, helping interpret the galaxy's motion. This meticulous examination of redshift forms the foundation of efforts to unveil the universe's destiny. Recent advancements in observational capabilities have allowed cosmologists to obtain clearer images of the universe, leading to a surprising conclusion. The redshift of distant galaxies exceeds predictions. Not only is the universe expanding, but it is also accelerating. This acceleration poses a puzzle, as no observable entities can account for such a phenomenon. The answer lies in a hypothetical force named dark energy, presumed to counteract gravity. In the early stages of the universe, gravity dominated, binding galaxies together like particles on the surface of water. Approximately 7 billion years ago, dark energy and gravity reached a balance. But as the universe continued to expand, dark energy gained supremacy, leading to an accelerated expansion. Dark energy, now the dominant force, challenges the understanding of the universe's fate. To predict the universe's destiny, scientists must comprehend the amount of energy and matter it contains. The historical narrative of the universe revolves around the interplay between dark matter, the force that binds the universe, and dark energy, the force propelling it outward. While the Big Crunch theory was rooted in the assumption that dark matter dominated, recent suspicions suggest that dark energy might be far more potent. If dark matter prevails, the universe might collapse. But if dark energy reigns, a dramatic and violent end awaits. Dark energy, the force initially responsible for shaping the cosmos, paradoxically propels it towards destruction. The cosmic battleground between dark matter and dark energy holds the universe's ultimate fate in the balance. Should dark matter triumph, it could lead to a collapse, tearing apart solar systems and stars. Conversely, if dark energy proves victorious, its relentless expansion might shred the universe, dismantling matter to fundamental particles. This impending demise is a peculiar twist of fate, where the force that facilitated the universe's formation continues to drive it towards an enigmatic and destructive conclusion. To ascertain whether dark energy is prevailing in this cosmic struggle, ongoing research and observations remain imperative. To comprehend the fate of the universe, scientists must first determine the rate of its expansion. One of the most intriguing aspects of the universe is its continuous expansion, with every galaxy moving away from every other galaxy. When observing the night sky, distant stars, galaxies, and clusters of galaxies are all in motion away from us. This expansion phenomenon can be illustrated using a balloon analogy, where every point drawn on the balloon represents a celestial object, and as the balloon inflates, each point moves away from every other point. However, the crucial observation is that the expansion is not only ongoing, but is accelerating, signifying that the universe's size is increasing at an ever faster pace. The uncertainty lies in the exact rate of this acceleration. If the acceleration is significant enough, a dramatic event known as the Big Rip could unfold, leading to the universe tearing itself apart. In an effort to demonstrate the impact of dark energy on the universe's acceleration, Dr. Robert Caldwell conducts a creative experiment on Earth. Using a paintball gun mounted on a truck, he simulates how dark energy propels the universe outward, causing it to expand. The truck, subject to Earth's gravity, rolls downhill, analogous to the force of dark energy pushing the universe to expand. The experiment aims to draw parallels between the forces acting on the truck and those governing the cosmic acceleration. The paintball experiment measures the distance between paint spots fired at regular intervals to calculate the truck's acceleration. This data is crucial for understanding how gravity's force compares to dark energy's force in the cosmic context. The idea of the Big Rip emerged when astronomers discovered the accelerating expansion of the universe. While the precise degree of acceleration remains unknown, ongoing efforts in astronomy seek to determine the speed of this expansion and unravel the past and future evolution of the universe. The cumulative distance traveled by the truck in the experiment exhibits a parabolic shape, indicative of acceleration. The acceleration calculations align with the forces observed in space, reinforcing the notion that the universe is continually accelerating. The data implies that, similar to the truck's acceleration, the universe might be expanding at an astonishing rate. The experiment provides a tangible sense of the potential dramatic expansion happening on a cosmic scale. As scientists grapple with the intricacies of the universe's acceleration, the question lingers about whether this continual acceleration, akin to the truck's movement, will persist over billions of years. The uncertainty surrounding the acceleration threshold and its potential runaway effect adds an element of mystery to the future fate of the universe. The ongoing pursuit of understanding the forces at play in cosmic expansion remains at the forefront of astronomical research. The eventual fate of the universe could involve a dramatic scenario known as the Big Rip, where distant stars and galaxies are forcefully pulled apart from each other. This process would unfold over an immense time frame, approximately 50 billion years into the future. The prospect is intriguing and foresees a universe characterized by violence and drama, with stars, planets, and even atoms being torn apart. Visualizing the breakdown of atoms provides a glimpse into this cosmic upheaval. Everyday objects, like coffee cups, are solid due to the bonding of atoms. Zooming into the atomic level reveals a complex fabric of particles. If these particles were to move apart, the bonds holding matter together would disintegrate, leading to the dissolution of objects. In this vision, the universe's end involves a gradual disintegration, starting with the extinguishing of stars and galaxies, culminating in the tearing apart of atoms. From an observational standpoint, standing on Earth or any surviving celestial body billions of years from now, one would witness a dark wall approaching. As this wall encloses, stars and galaxies go dark, and eventually, atoms themselves are torn apart. This process reduces the universe to a shrinking point, marking the conclusion of its existence, according to the perspective presented by Robert Caldwell. The ongoing quest to unravel the cosmic acceleration and the role of dark energy adds an element of mystery to this narrative. Dark energy, often associated with the acceleration of the universe's expansion, is a significant player in this cosmic drama. It is the focus of scientific inquiry, akin to a detective story, where researchers aim to identify the culprit behind the accelerating universe. Named dark energy, its properties and mechanisms remain enigmatic, requiring more information to fully understand its impact on the fate of the universe. While the Big Rip is one theoretical scenario, the Hubble Space Telescope offers insights into alternative possibilities. Depending on the rate of acceleration, the universe might face a less violent outcome, such as the Big Chill. In this scenario, the universe would continue to expand, but at a slower rate, eventually becoming dark, cold, and devoid of life. The Hubble Space Telescope, with its unobstructed view of the cosmos, has been instrumental in providing clarity and detail to scientists, aiding in their predictions about the universe's eventual destiny. The concept of the Big Chill is grounded in the influence of dark matter, another mysterious component of the universe. Dark matter, often considered the cohesive force maintaining the universe's structure, could act as a counterforce to dark energy. If dark matter remains constant, It might counterbalance the accelerating effect of dark energy, leading to a scenario where the universe gradually cools down and enters a state of stillness. In summary, the fate of the universe remains an intricate and evolving narrative, with multiple theories vying for prominence. Whether it's the dramatic Big Rip or the gradual Big Chill, scientists continue their exploration, using tools like the Hubble Space Telescope to unlock the secrets of the cosmos and better understand the forces shaping its destiny. To avert a catastrophic event like the Big Rip, astronomers seek evidence of dark matter, a mysterious substance believed to exist based on certain anomalies observed in Hubble's images of nearby galaxies. In some instances, these galaxies appear to be surrounded by others, but these surrounding galaxies are actually optical illusions, reflections of more distant galaxies. This phenomenon, known as gravitational lensing, occurs when the curvature of space, influenced by stars and dark matter, bends the light from distant galaxies. The degree of bending in gravitational lensing provides astronomers with a valuable tool to measure the distribution of dark matter on various scales. By analyzing the distortion in background galaxies, scientists can map the presence of dark matter and observe how the universe behaves around it. This process involves studying the light from distant galaxies passing through clumps of dark matter, allowing astronomers to deduce the gravitational forces at play. The challenge lies in distinguishing the dominance of dark matter or dark energy in various regions of the universe. The ongoing debate centers on whether a Big Chill or a Big Rip will mark the fate of the cosmos. Current evidence suggests that dark energy is the primary driving force, but the magnitude of its influence remains a key mystery. Determining which force, dark matter or dark energy, prevails in specific regions can provide crucial insights into the ultimate destiny of the universe. Measuring the speed of the universe presents another obstacle. While determining the speed of objects on Earth is straightforward, the vast distances and time spans involved in cosmic observations make it challenging to precisely gauge the speed of celestial phenomena. However, advancements in imaging technology, particularly clearer images from space, offer astronomers a more accurate means of estimating the universe's rate of expansion. As scientists work towards solving this cosmic puzzle, they contemplate scenarios like the Big Chill, where the universe expands continually, leading to the depletion of nuclear fuel in stars. In a Big Chill, distances between stars become so vast that they nearly disappear from view, and the universe descends into a frozen state. Earth, as part of this expanding cosmos, would eventually freeze and become devoid of life. The once vibrant universe transforms into a cold, dark, and lonely expanse. While newer stars may persist, most would have moved beyond observable distances. The inexorable expansion, coupled with the depletion of energy sources, paints a picture of a universe gradually fading into darkness and coldness. This vision suggests a lonely future, with neighboring galaxies receding beyond visibility, leaving a frozen remnant of the universe's former vibrancy. In this pursuit of understanding dark energy and dark matter, a probe in deep space contributes valuable information, offering fresh insights into the cosmic forces that shape the destiny of our universe. The quest for knowledge continues as astronomers unravel the mysteries of the cosmos, striving to decipher the intricate interplay between dark matter, dark energy, and the fate of the universe. Scientists are advancing their understanding of the universe's history and ultimate fate through groundbreaking initiatives in big science. Although the night sky may appear serene, underlying forces are propelling it towards an inevitable conclusion. A key player in this cosmic exploration is the WMAP, Wilkinson Microwave Anisotropy Probe, a NASA satellite providing astronomers with unprecedented insights into the early universe. The mesmerizing multicolored image captured by WMAP serves as a map of the early universe, portraying the remnant heat from the Big Bang. This ancient light, considered the oldest observable in the universe, divulges crucial information about the universe's composition, expansion rate, and initial conditions. WMAP's ability to measure temperature differences in the cosmic microwave background holds the potential to unravel the dominant force shaping the universe and predicting its ultimate destiny. The blue and red spots in the WMAP image denote regions with slightly colder and hotter temperatures, respectively, revealing temperature differences originating from the Big Bang. These variations enable scientists to analyze not only the substance within the universe, but also its potential fate. WIP's precision is noteworthy, capable of detecting temperature differences as minute as 1/1000 of a degree. This high sensitivity aids scientists in calculating the ratio of dark matter to dark energy, pivotal factors influencing the universe's eventual outcome. The process involves assembling the multitude of temperature measurements into a comprehensive map that highlights variations against the uniform glow of the Big Bang. Adjusting the contrast brings the WMAP image to life, providing scientists with a tool to explore the universe's fate by delving into its distant past. Analyzing WMAP imagery entails a captivating journey back through space and time. Departing from the probe, one traverses celestial bodies like Mars, Jupiter, and Saturn, each contributing their reflected light to the journey. Passing the Milky Way in Andromeda, the next nearest galaxy, whose light takes 2.3 million years to reach us, the journey reaches back 13 billion years to the inception of visible light. WMAP's ability to peer into this distant past confirms crucial aspects of the universe's evolution and contributes to predicting its eventual demise. Combining WMAP data with astronomical observations has led to groundbreaking discoveries about the universe's rapid expansion, supporting the dark energy theory. Recent findings indicate a dominance of dark energy over dark matter by a factor of 2 to 1. This evidence propels astronomers into a realm of new thoughts about the universe's origin and end. The era before the revelation of dark energy was characterized by simpler assumptions, where determining the amount of matter in the universe seemed sufficient to make predictions about its ultimate destiny. The days of simplicity in understanding the universe are behind us, but the accumulating evidence strongly supports the notion that the universe will persist in its expansion. This progress, achieved over the last century, has deepened our insights into the universe's evolution and expansive nature. However, this newfound knowledge has also given rise to more complex questions than we've been able to answer thus far. Looking ahead, the next decade promises even more excitement as astronomers confront numerous challenges presented by theorists. The journey into unraveling the mysteries of the universe is marked by constant exploration and testing of hypotheses. While significant strides have been made, the field of astronomy is now at the forefront of addressing various challenges. The coming years hold the potential for groundbreaking discoveries as scientists grapple with questions that push the boundaries of our understanding. The excitement lies in the ongoing pursuit of knowledge through observation and experimentation, which is the essence of scientific inquiry. The ongoing cosmic battle between dark matter and dark energy, anticipated to extend over billions of years, will unfold long after humanity has disappeared from Earth. Despite our transient presence, the pursuit of understanding the universe's origins, mechanisms, and ultimate fate remains one of the most significant endeavors in the realm of science. This perpetual quest not only drives astronomical research, but also fuels the human curiosity to uncover the profound answers to questions about the fundamental constituents of the universe and the enigmatic destiny that awaits it.